So let's start with the definition of interior point. Let A be an element in a subset W of R, then A is said to be an interior point of W if there exists a neighborhood N of A such that A is in N and N is wholly within W. Example: in our last class we have taken the example of open interval 0 1, and we saw that the set N is a neighborhood of each of its points. So each point of N over here is an interior point of this set. Each point of N is an interior point of N, because if we take any element from the open interval 0 1, then we have seen that there exists an open interval CD by density property such that A is in the open interval CD and the open interval CD is wholly in the open interval 0 1, and here the open interval is a neighborhood of the point A. If we also have taken the semi-open interval 0 1, but we also saw that the set N is not a neighborhood of the point 1, and we can say that 1 is not an interior point of the set N, because if we consider an open interval city containing 1, then the open interval, that is a neighborhood of 1, is not fully contained in the set N. So 1 is not an interior point of the set N. Now we consider these two examples. The first one says that each point of the set N is an interior point of the set, but the second one, not every point is an interior point of N. So this type of sets have more importance. So this leads to give the idea of a new concept, which is open set, because of these properties. So a set in which every element is an interior point is called an open set. So for example, this set is an open set, but this set will not be open set because one point is not an interior point of this set. And formal definition is a set G, which is a subset of R, is said to be an open set if each point of G is its interior point. Take example, the set R itself. We claim that the set R is an open set for, we take any arbitrary real number A. Now we have to find a neighborhood of the point A, which will be only in the set R. So we can take any open interval, open and bounded interval containing A. So C and D. So how can we choose C and D? There are so many methods. So let us take C as A minus 1, D as A plus 1. In that case, we find that A minus 1, A plus 1 contains the element A, and this open interval is only contained in R. So we see that the point A is an interior point of R. Since A was chosen arbitrarily from R, so each element of R is an interior point. So the conclusion is that R is an open set. What about the set n of all natural numbers? So first of all, we plot the elements of the set 1, 2, 3, 4, etc. Now take any arbitrary point. Suppose we take the point 3, and if possible let there exists a neighborhood n of 3 which is wholly contained in the set of natural numbers. But by the definition of neighborhood, there exists an open interval in between 3 and n. So there exists an open interval CD containing 3 which will only contained in the set n, that means neighborhood, which will be only contained in the set of all natural numbers. Now we see that is 3 belongs to CD. CD is only contained in the set of natural numbers. This set is uncountable. This set is countable. So this relation is not possible. So there does not exist any open interval CD such that it contains 3 and it is wholly contained in the set of all natural numbers. So 3 is not an interior point of n. Thus the conclusion is that the set n of all natural numbers is not an open set. Not an open set.